Hello everyone. Let's understand Flajolet-Martin algorithm, in short FM algorithm. Now this algorithm is also called as a counting distinct element problem in stream, also cardinality estimation problem, which is nothing but finding number of distinct elements in the given data stream. So what do you mean by counted distinct element problem in a data stream, and how we solve it using FM algorithm, that we will see. These are the two questions that were asked in exam. Now here the algorithm is not directly asked. Here the question is count number of distinct elements in the given data stream, or explain count problem with suitable example. That means indirectly they're asking us to explain FM algorithm. So this is what you need to remember, that even if the question is not directly asked with FM algorithm, it may be in a way they're asking you to count distinct elements in the data stream, which is indirectly your FM algorithm. So what exactly is a counting distinct element problem? So it's a very simple algorithm that helps us to find out the distinct elements in the given data stream, which requires very large amount of memory. It is one of the probabilistic algorithms that we use, in which we are using hashing functions, randomization functions to get an approximate count of the data. Here we are talking about data streams, and we know that data streams are infinite data, unbounded data. So we can't see the entire data together at a time, and that's why we are only dealing with a part of data, and that's why the value that we get, it is only approximate value. Please remember, the value is approximate value and not the exact value. So in an applications where you need the exact count, there you can't apply this particular algorithm. This algorithm is only going to give you the approximate count, the nearby value to the actual value. So that we have to remember. These are a few applications where we can use this particular algorithm. So let's say I want to find out the unique visitors on my website. I can do that using this particular algorithms. I can know that who are the unique visitors who have visited the website. I can find out unique IP addresses. I can find out unique elements in the given large data sets. So wherever there is a requirement to find out unique elements, that too approximate answer will also work. Then we can go for FM algorithm. Okay. Now here, this algorithm is very useful if where the size of the memory is too large, and we can't process the entire data in a complete one go. So we can use this particular algorithm in such cases. Here we consider a set as an universal sets with the elements coming from all the data streams, right? So there are various sources from where we are getting the data streams, and we are considering that as a universal set. Take an example of login sites. So we can consider login sites are all the login sites are universal data set, which has all the information related to all kinds of logins. So means the usernames and their passwords. Like for example, Facebook, Twitter, Instagram, right? So all these media, these are all login websites where there are a number of users, and every user has their own login credentials, right? If you talk about Google, then Google's universal set will be all the IP addresses of all the web pages. Now here, the counting distance problem takes two approaches. First approach is where we consider that all the elements, they reside in the main memory, and we are arranging these elements in such a order that we create a specialized structures to store all these elements. So let's say I'm using a hash table, or I'm using a search tree, and I'm storing my information into these structures. So whenever I want to, whenever let's say a user visits a site, we are going to check if that user's entry is present in our table or our search tree. And if it is so, then we are not going to add that entry to the database, right? So if the entry is not there, then only we are going to add that entry to the hash table and the search tree. If the entry is already there, we are not going to do anything, right? That means we know that that user had already visited the website earlier. So that is how you can create unique entries in your table. So this hash table will have all the unique entries or search. Now the problem here is when the number of users starts increasing exponentially. So with the use of Facebook, Twitter, Instagram, right, the number of users have started increasing exponentially. So in that case, it's impossible, it's not possible for us to maintain that big hash table in the memory or a search tree in the memory. So our data, we started assuming that our data is not fitting into the main memory. right? And if these streams of data we need to process in the real time or at the same time coming from various sources, so it's difficult, and that because of that the performance will get degraded. So what are the other approaches then? Because we can't store everything in the main memory, so then we can go for the second approach where we can have a compute nodes, and we can use the concept of Hadoop or distributed computing to perform the same action. But you can see that there is a hardware complexity that is getting added into this problem, right? Because there are multiple nodes you have to apply for, go for parallel processing, and multiple nodes, that means multiple clusters, and then their infrastructure installation and server management, everything comes into picture. Third approach is we can use a normal secondary memory. So as and when we require, we use secondary memory and we store our data into the secondary memory. But again, that is also time consuming. Anything that goes into second memory will never be real time application. So these are few problems that comes with when the data starts increasing and we're not able to fit our data into main memory. So here the efficient approach is we're going to use Flajolet Martin algorithm that uses just a small amount of memory, main memory, and that uses a concept of probabilistic algorithms to get the approximate number of unique elements from the data set. And the data set that we're talking about is not the entire data set or not the entire data stream, but the part of stream that we have seen so far. Now, how it exactly works? So we use it to estimate the number of unique elements in the stream over a single pass. So we just need a single pass to estimate the number of unique elements. Here we get an approximate number. We are not going to get the exact number. Now, if we have total n elements in the data streams, and out of those n elements, if there are m unique elements, so in short, this algorithm takes big O of n time to run to get to find out the m unique elements, and the total amount of space that is needed to store those unique elements is big O of log m memory, right? And this algorithm is suitable for real-time applications also. The only disadvantage is it is going to give you approximate count, not the exact count. Now, what exactly, how exactly this particular algorithm works? So it uses hash functions. So we may have one or more adequate hash function that we can use, which will help us to map our input to a value that will be converted to a bit array. Right, so we are getting a input that will be mapped to a number, which will be later on converted to bit array, and that the size of bit array may vary depending upon how many bits you want to represent for that number. 64-bit is large enough to store any particular uh, uh, you know uh, distinct elements in your data stream. Now, once you get these bit arrays, what we do is we find out the trailing zeros. So we will find the trailing zeros from that bit array. So the step is we take a hash function, we map our input to the n elements to get the bit value which is locked to the base 2n bits. Once we get these bits, we find the trailing zeros, which is R of A. Once we get R of A, we find out the maximum R from these R of A. So capital R is the maximum R of A that we have seen so far. And once we have R, we estimate the number of distinct elements, which is nothing but 2 to the power R. So for example, if R of A is position of first one counting from right, then H of A is, let's say, 12, then trailing zeros are nothing but 2 here, because this is the first one starting from right. That means 2 are the trailing zeros that I'm seeing so far. That means my R of A is 2. And if 2 is the max value, then 2 raised to power 2 will be 4 distinct elements that I'm getting. Right. Now let's try to understand it with a simple example. These are the distinct elements in a stream. Let's say these are the elements in the data stream, and I want to find out the distinct elements in the data stream. This is the hash function that we have chosen for this particular problem. Now, what you need to do is take each input value, map it to the hash function to get a binary number, to get a value, right? So key value. So for one, if we map that one to this hash function where x is 1, we are getting value as 2. Right, so 6 into 1, which is 6, 6 plus 1, 7, 7 mod 5, which is 2. So I'm getting 2 as a value that is been generated from this map function. Now, similarly, you can do it for all the remaining values. So 3, 2, 1. You need to write them down. The values may be repetitive, but you have to write them down again. Right, so you are going to create this kind of a table where you will write the values, the hash value that you got for those particular keys. Now, once you have the values, that means the number, n element, you're going to convert it into binary bit. So you're going to calculate the binary value for that. Now the number of bits you can decide on your own depending upon what value you are getting as an output. So you can see the max value that I'm getting for any hash for after hashing a key, it's 4. So I know that to represent 4, I can represent it with 3 bits. So I'll write 100. That means 3 bits are sufficient to write all these values. So what I did is I passed the input value to the hash function, which generated a hash value. I will create a binary bit array for that hash value. Now, once you have a binary bit array, find out the number of trailing zeros. Now, trailing zeros are means what do you mean by trailing zeros? So from right when you start, you have to find the first one. So before that, whatever comes, those are the trailing zeros. So from right, this is the first one that I'm getting, means there is single one trailing zero that I'm getting. Here, two trailing zeros I'm getting. Here, there are no trailing zeros because this is the one I got, but there are no trailing zeros. Again, one trailing zero, no trailing zeros, two trailing zeros. Now here, if you see, there are no one only. So if I start and search for one to the left, starting from right, there are no ones here. That means there are no trailing zeros. These are all zeros, but they are not trailing zeros. And that's why the answer for this will be 0. Then again 0, 2, 1, 0, 0, 1. So you need to write down these trailing zero values for these functions. So as I said, as I mentioned earlier, these are the number of trailing zeros. So just write them, write them. Okay, so these are the trailing zeros which I have written. So just you have to be very careful with these kind of conditions where all are zeros, means there is no trailing zero because there is no one from the right first one I'm getting, and that's why the answer is 0. Okay, if nothing is there, that is also considered as 0. Now once you have this, you are going to find out the max trailing zeros. Now among this, the max value is 2. So I can clearly see that the max value is 2. Therefore, R here is 2. R of A is 2. And because R of A is 2, that becomes our max value. So 2 to the power R, which is 2 to the power 2, which will be 4 here. So I'm getting 4 distinct elements in the given string. So you can see that this function is chosen very correct because I'm getting the exact value of the unique values from the data string. Right? So it's very important to choose an adequate function that will give you the very near value to the actual value. It may be not the actual value, even if you're getting 5, 6 for that matter, is also a good one, good number, because as I mentioned earlier, it is not going to give you the actual value, but only the approximate value. So these are a few examples again. Like for if you see this, these are the streams given, and there are two hash functions. So if I want to know the adequate function among these two, I need to do the same process. So let's say I'm doing it with using the first hash function. The same thing, whatever input values you got, just map it to the hash function, get the value out of it, and convert it into bit array. Now here my bit array is of 5-bit size because the maximum number is 25. So for 25, I can represent it with 11001. And that's why I've used 5-bit numbers. So this is my 5-bit array. And then you find out the trailing zeros. So there are no trailing zeros in the first number. Again, no trailing zeros, which means 0, 0, then 1, 1, 1, 0, 4, 2. So 0, 0, 1, 1, 1, 0, 4, 2. So these are the trailing zeros. Find the maximum trailing zero, which is 4. And because R is 4, so 2 to the power R, which is 2 to the power 4, 16. Now 16 is the approximate number of distinct elements in the given string. You can clearly see that this is not very near to the actual value. So it may not be an adequate hash function. Let's go with the second one, x plus 6 mod 32. So if you solve using x plus 6 mod 32, after you get the bit array and after you get the trailing zeros, you will find the trailing zeros are 3 max value. So 2 to the power 3, which is 8. And you can see 8 is clearly the very close value to the actual distinct element. That means this function is adequate function. So here the thing is that you need to have a very adequate, function which you have chosen very wisely to get the correct number of unique elements. So why FM is good? Because of its scalability. right? Because it is able to tackle the large data sets and it estimates the number of unique elements without having to use the main memory or the entire data set in one go. Second, memory efficiency, because it demands minimal memory. That's why it uses hash function and bit arrays to effectively find out the unique elements. Also the speed, it is suitable for real-time application. So it's computationally very efficient and it generates the result in real time or on the fly calculations. The challenges in this is, as I mentioned earlier, hash function. What hash parameters you are using and how the values are passed to these hash function, that is going to prove whether your algorithm is efficient or not. Okay, so here the number of hash function that you're going to use also matters, and which hash functions you are using also matters a lot in making this algorithm a efficient algorithm. So this is FM algorithm. Thank you.